Well, good afternoon and welcome to another video lesson. Today we're going to be discussing section 4.5. Section 4.5 is on two very important topics. One of them is the idea of linearization, and the other is what is known as Newton's method. Both of these are applications of the derivative, but in a very different way from the optimization problems where we were trying to minimize and maximize things. Here we'll be making use of the derivative to help us model and find different kinds of points on curves. So let's begin with linearization. Both of these topics that we're going to be discussing today are topics that came about as a result of the fact that computations are very tedious and difficult to do. Nowadays we have graphing calculators, we have computers, we have all sorts of ways of making computations easier, but in the past that was not always the case and problems could become very difficult. So the goal of linearization is to provide a local, so in a small region, provide a local linear model of a curve. And this comes all the way back to the ideas of differentiability. Remember that for something to be differentiable, it has to be continuous and smooth. It has to be locally smooth. If we think about a particular function, and we think about the behavior of that function on smaller and smaller intervals, if the function is differentiable, then we must have it approaching a straight line. It has to be starting to look more and more like a straight line. We can consider some strange function that looks something like this, and we can even pretend that we can zoom in. We can look at closer and closer points, maybe to right here. If we zoom in on this particular part of the function, what we see is that we have a curve that looks something like this, and if we continue to zoom in, what we find is that eventually the function starts to take on a more linear shape. And this is a very important and powerful tool. Oftentimes in economics and sciences, we're dealing with very complicated models that are very difficult to solve. So linearization allows us to take a very complicated situation and look at a small region of it and treat it as though it were a straight line. And of course, straight lines are very easy to work with. We have a lot of experience with those. So let's talk about the idea of linearization and let's see how this actually works. So first of all, let's recall the equation for a line. So let's focus here on the point slope form for a linear equation. And again, if the slope here is m and a point on the graph is x1, y1, then the point slope form of a linear equation will be y minus y1 is equal to m times x minus x1. Now we're going to use this form, or a slightly different version of it. Maybe we will rewrite this as y equals m times x minus x1 plus y1. We will use this particular formula to come up with a linearization of a particular function. So let's suppose that we want to do this, and you already have experience with building linearizations, because a linearization is nothing more or less than a tangent line to a curve at a point. That's really all we're working with here, but we're going to formalize it a little bit, and we're going to come up with a general formula. So suppose we have some curve, and we have some point on that curve, and let's call that particular point the point A, comma, f of A. What we would like to do is we would like to find a linearization of the function about this point. And what that means is that we would like to come up with a line that models that point in a nearby area. So something that looks like this. So what do we need to know? To come up with the tangent line, we have to know what the derivative is. So the slope of this line the slope of this line is simply going to be the derivative at that point, at that x value, x equals a. And now you see we have the slope and we have a point on this line. So we can come up with the linearization of this function. So we're going to call this L of x. This is the linearization of this function. The linearization is going to be the slope, which is f prime of a times x minus a plus f of a. And this is really just the point slope form that you are used to here, right? This is the slope, this is x minus x1, and this is plus y1. So we have the general formula for the linearization of a function right here. This is a very nice kind of function to be able to work with, and it has some power besides just modeling things. Let's go ahead and find a linearization first, and then we'll see some other applications of this particular tool. So let's start by doing an example here. We will find the linearization of the function f of x is equal to 1 over x at x equals 5. So here we have a curve, right? The function 1 over x is a rational function. We have a curve. We'd like to find out what an approximation for this function would be at x equals 5. So first of all, we want to know what the value of the function is at this point, and we can see that the value here is going to be 5, 1/5. Right? Those are the values of the function here. Then we want to figure out what the derivative is, so we know what the slope of our linearization will be. The derivative of 1 over x is minus 1 over x squared. So the derivative when x is 5 will be minus 1 over 25. Okay, minus 1 over 25. And if we plug these in now to our linearization, the linearization of this function, then recall, is f prime of a times x minus a plus f of a. And in our particular case, then, that will be f prime of 5 times x minus 5 plus f of 5. So the result here is the linearization, the linear model of this function, is going to be minus 1 over 25 times x minus 5 plus 1/5. And we call this the linearization of 1 over x about x equals 5. And the about here simply means that that's the point on the line, that's the point on the curve rather, that we are finding the linearization of. So this models the behavior of this function in a small region, of the graph there. And we can use this, if we would like, to come up with values. So for example, one of the applications we can use here is we can use this to approximate values. So let's suppose we wanted to know what the value of the function were at the point x equals 5.5. We could just plug this into the original function and have 1 over 5.5. So over here, maybe we will take that and we will say that just for the record, f of 5.5 is, that is the number 0.1818. So 0.1818 is the actual value. It's a repeating decimal, but we're going to approximate it, and we're going to approximate it by plugging 5.5 into the linearization. So we're going to see what happens if we plug 5.5 into the function up above. Well, that's going to give us minus 1 over 25 times 5.5 minus 5 plus 1/5. And this is a big mess, right? This is not something that you guys love to do because it's so tedious, right? It's much easier to just plug things into your calculator and get the answer out, but recall that this is a tool from a time when calculators were not so common, and so we ended up having big differences there in what we could do. So this, if we evaluate this now, this becomes minus 1 over 25 times 5.5 minus 5, just becomes 0.5 plus 1/5. Okay. We can go through now and work things out a little bit. Minus 1 over 25 times 0.5 is going to be half of 1/25, so this is going to be minus 1 over 50 plus 1/5. And turning these into decimals, minus 1 over 50 is the same as minus 0.02, and 1/5 is 0.2. So you can see that the linearization of 5.5 is 0.18, which is fairly close to the original answer, the actual result. So linearization is a powerful tool. It's more powerful the closer you are to the original point, and it's also more powerful for graphs that have fewer curves, right? Those curves tend to change things a little bit more.